Hi there. Welcome to another edition of Mr. Weis Solves an Old AP Calculus Problem. So this time we're working with the AP Calculus BC 2010 number 4. This is all about integrals and volumes of revolution and volumes where the base of a slice by slicing, etc. A difference between the areas of two curves. So actually that's how it begins. Here we're given two functions. Y equals 2 times the square root of x. That's this one that's swooping up right here, and the line y equals 6. They give us this graph, and they tell us that these two curves intersect at 9, 6. It's not too hard to check. If you plug in 9 for x here, you're going to get 2 times root 9, which is 6. So they do indeed intersect there. And in part A, we're supposed to find the area of this region R that is between these two curves, starting at the y-axis. So we want, for part A, we want the area of R. So this isn't too difficult. If I go and I pick I pick an x in the range of values where x is allowed to happen, so that seems to be anywhere from 0 to 9. It seems like regardless of where I choose my x, if I were to follow it up, I'd get a nice representative rectangle that looks like so. And what I would generally do is add up the areas of all of these little tiny rectangles and take the limit as the number of rectangles go to infinity, and we'd end up with a nice integral here. What's important ultimately, it becomes the height of those rectangles, which you can see the height is always the top function, which is y equals 6, minus the bottom function, which is y equals 2 root x. So therefore the area of R is simply the integral from wherever x is allowed to start to where it ends, in this case 0 to 9, of the top function, y equals 6, minus the bottom function, 2 root x dx. And now we simply have to compute this integral, which shouldn't be too hard. This is the integral. Antiderivative of 6 is 6x. The antiderivative of 2 times x to the 1/2 is 2 times x to the 3/2, and then I guess I need a 2/3 down here to cancel, and I'm going from 9 down to 0. So let's see, this ends up being 54 minus 4/3 times 9 to the 3/2. Let's see, so I'm going to choose to take the square root of 9 first, which is 3, and then cube it, which is 27. So we have 54 minus 4/3 times 27. Of course, 27 divided by 3 is 9, so this is 54 minus 36, which I think is 18. And so 18 square units, and that's my final answer. Okay, so here we are doing part B of the 2010 AP Calculus BC exam number 4. We were dealing with these two functions, y equals 2 root x and y equals 6. They create this nice region with the y-axis here, which we're calling R. And in part B, part A, we found the area of this region. In part B, we're asked to find the volume of the solid generated when this region is rotated around the line y equals 7. Interesting. So here's the line y equals 7. I'm going to make a little dotted line here. And what we want to do is we want to rotate around that line. So in order to figure out what I'm going to need to do here, I'm going to draw a representative rectangle and try to figure out what I should do. So I think I'm going to be able to use the x-axis here and rotate like so. So if I grab a random x in the range that I'm interested in, such as this right here, I see that if I follow that up, I get a nice representative rectangle right here. Now that nice representative rectangle is getting rotated around this axis, and it ends up here looking something like this. It's a little too big. It ends up here looking something like this, where this went like that, and then it came back around. like so. And then this part also went all the way around like so. And this part went around like so. And we end up seeing that, I'm not going to draw the rest of it, but we see that we have some nice disc here. A washer actually is what this is called. What we're interested in when we're finding the volume using washers is we're interested in two radii ultimately. We need to know the smaller radius and the larger radius. So the radius is always taken with the axis that we're rotating around. So I believe our smaller radius is just going to be that length right there. That's playing the role of little r. In general, little r might depend on x, though I think if we think about it in this case, that's not actually happening. And then we have our big radius, which is that thing right there. That length is our big R. Now, on the other hand, big R does seem to depend on where I chose x. I can see, for example, as x gets bigger, closer to 9, that the larger radius, big R here, that's a little confusing if I call that region R. Big R here is getting smaller. Okay, so I think we're ready to set up our integral then. This should be pretty straightforward. The volume equals pi times the integral. And the reason pi comes in is because really what we're doing is we're finding the volume of this little washer, and we're going to find tons and tons of them, add up all of those little volumes, take the limit as the delta x goes to 0, the delta x will become a dx, the sum will become an integral just like it always does. And so here this becomes the integral of pi times the larger radius. So the larger radius is ultimately that purple distance right there, which is 7, the entire distance, minus that. But that distance is just 2 root x. 7 is the whole distance down to the bottom of the x-axis. Minusing this much right here will give us the capital R we're interested in. So I think it's 7 minus 2 root x squared, capital R, that's our r squared, minus our little r squared is 7 minus 6, which is always 1 in fact. So I'm just going to put minus 1, that's our little r squared, and this is dx, where x is allowed to range from 0 to 9. And there you have it. This is the integral that we end up having to compute. So I'm going to go ahead and do that right now. So let's see, this equals pi times the integral from 0 to 9. I'm going to go ahead and multiply all of this out and see what we end up getting. So, oh man. So that's going to be 49, let's see, minus 14 times 2, which is 28 root x, plus 4x minus 1 dx. So that ends up being pi times the integral from 0 to 9. 49 minus 1 is 48, minus 28 root x plus 4x dx. And so here we go. This ends up equaling pi times 48x, easy antiderivative, minus x to the 1/2 becomes x to the 3/2, but we have to bring down a 2/3. So that's 2 times 28, which I think is 56 thirds x to the 3/2. And then plus the antiderivative of x is x squared. We're going to need to make that become a 2 in order so that that will work out. And then that goes from 9 down to 0. So now I plug in 9 and we get pi 48 times 9 minus, I'm going to do the same thing we did last time. So I plug in 9 to the 3/2 here. This really becomes 27, but there's a 3 in the bottom, so that's actually 9. So it's 56 times 9 plus, and then this ends up becoming 2 times 81. And then it's minus 0 since there's an x in all of these cases. Now a thing to notice here is I have 48 9s minus 56 more 9s. So altogether, how many 9s do I end up having? Here, 48 minus 56 is 8 9s, I believe, so a negative 8 9s. So I believe I have negative 8 times 9, plus, in fact, if we want, I can think of this as 18 nines. These are things that people, like a math person, will do to save time when I'm not using a calculator and stuff. Now, of course, if I had a calculator for this, I'd just plug all this in there. So I think, in the end, I have 18 nines minus 8 nines, which is a total of 10 nines. So I believe the answer is 90 pi. And I sure hope that is correct, because that was a fair amount of work there. Okay, so here we are in the final part, Part C of the AP Calculus BC 2010 number 4. We've been dealing with this region R, which is bounded by these two curves, y equals 2 root x and y equals 6, and the y-axis. You might notice that I've drawn this a little bit strange this time. That's because this problem has to do with an area by cross-section, so I'm going to read it actually. The region R, which was the base that we've been, which was this area that we have been dealing with for the rest of this problem, is now the base of a solid. For each y going from y equals 0 to 6, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base in region R. Write, but do not evaluate the integral. Actually, on the last problem, it turns out I wasn't supposed to evaluate that one, but I did it anyway. I'll probably evaluate this one too, just because I can't help myself. But there we go. So that's what's happening. So I drew it this way so maybe we can more easily see what's happening with our solid. So again, now we're doing perpendicular to the y-axis. Everything else I'd been doing perpendicular to the x-axis. So let's say that I take my y to be right here. What's going to happen is we're going to form there's my representative rectangle, looks something like this. But now that representative rectangle turns into a 3-dimensional solid that comes up like so, and whose height is 3 times the base of that thing. If I took my y over here, it would end up coming up into a solid whose height is really, really tall. It's supposed to be 3 times the height of that thing. So I don't know that I'm making it be that accurate like that, but that's what's supposed to happen here, and I'm supposed to get this little solid. And that's happening at all of the y values that you can possibly pick. And what we're going to do is the same thing we always do. We're going to break this interval up into a bunch of regions. It's the y-axis that we're breaking up. We're going to have these little rectangles that are then going to give us little volumes. These are called rectangular prisms. And we're going to add up the volumes of all of these rectangular prisms and then take the limit as the size of our little rectangles goes to 0, or equivalently as the number of rectangles goes to infinity. And our sum symbol will turn into a sigma, or will turn into an integral symbol, and any delta y's or delta x's will turn into dy's and dx's. So the only thing that becomes important for us to figure out then is what this, what the area, or it's actually like a little volume of these little rectangular prisms are. So let's look at one of these guys. Let's maybe zoom in on one of these guys. So note that this distance right here is my delta y. That's the thing that's going to turn into a dy. This distance right here depends on y. You tell me what y is, and I'll tell you what that distance is. Note, though, that that distance is actually an x. That should not go straight down like that. That should go like this. You tell me what you tell me what y is, and I will tell you what that length is. But note that that length is actually an x distance. So one of the first things we're going to have to do is solve this for x in terms of y. And so if I square both sides of this, I'm going to get that y squared equals 4x, so x equals y squared over 4. And so that's how long that is. You tell me what y is. This length is y squared over 4. Here it's y squared over 4. For small y's, you get a small y squared over 4. For large y's, you get a large one. Now, this length is 3 times the base. So that's going to be 3 times y squared over 4. And that's what this one is going to be too. 3 times y squared over 4. Now what do I want to do? I want to take the integral The volume I'm interested in is the integral as y goes from the smallest thing it's allowed to be to the largest thing it's allowed to be, in this case 0 to 6, of the base times length times height. So that ends up being y squared over 4 times 3y squared over 4 times delta y, which becomes a dy. And so this ends up being our integral. So we're doing 3/16 times the integral from 0 to 6 of y to the 4th dy, which we can stop here, but why not just finish it really quickly. This is going to be 3/16 times 1/5 y to the 5th from 6 down to 0, which ends up being 3 times 6 to the 5th power over 16 times 5, which if I had a calculator or felt like computing, I could totally figure out what this number is. This is in cubic units, it's an actual volume. But that is my final answer.